Okay, for those who already inside the meeting, can you hear my voice? All right. Okay. Okay. Thank you for your response. Okay. So I'm sorry because of the technical issue and also about the connection. So I need to off my camera. Okay. So there is no video input for this meeting. Okay. Since it grab huge data, or maybe it create some disturbance in the connection. All right. Okay, we will continue our lecture today for inherently safer design. Okay, and we will look further what is the four method that we already been discussed. Okay, last week. Okay, I hope that today we can finish the topics. Okay, this inherently safer design. Okay, before we going for process safety management. Okay, after your hari raya breaks. Okay, we try to wait for your other friends. All right. Okay. Okay. We try continue our lecture today. Okay. So for today, I will make a summary. Okay. We will try to start back. Okay. From the start. What is ISD? Inherently safer design. Okay. So while your friends still coming in, it's okay as long as you already sign up for your attendance. All right. So in release safer design for plant safety. So place a pointer. Okay. So the objective of inherently safer design solution is to uh, to make you enable to develop your own ISD analysis for engineering components. Okay, the first one for engineering components together with your chemical processes. So the combination of engineering components and also your chemical processes will contribute to your development of your plant design. Okay, you already have developed your own plant design, right? For your integrated design. Okay, so from your integrated design project, you can develop your ISD solution. Okay, you can create your inherently safer design solution for your plant design. All right. Did you receive any task regarding your integrated design for this semester? Have you received your task for You can see 338. Okay, 2 already. Okay, so you only wait for 367, right? All right. Okay. So never mind. Okay, I will give you the clue. Okay, you will develop your ISD and also your hazard. Okay, for your plant design. Okay, but the question I will release only after Hari Raya break. All right. Yeah, deadline is surely. I will give you sometimes. Okay, never mind. Okay, I will give you times since you cannot make a consultation with me face to face, so the due date will be prolonged. All right. So this is the objective of the topic. Okay, to develop ISD solution for plant design. Okay. So the topic online is what is ISD, why you need ISD, and how to implement ISD. Already been discussed. Okay, we already discussed all this issue. Okay, the issue of why you need ISD and what is ISD is actually already been covered in the article that I give you. Okay, so basically the article talk about what is ISD, what is the four methods of safety, and why you need the ISD. Okay, however, the article actually is half of what it is. Okay, the remaining of the articles talk about how to implement ISD using minimization, simplification, substitution, and also uh, moderation. Okay, so our task is to implement this ISD towards the process. Okay, towards the process and also the equipments. It's either reactor, relief valve, heat exchanger, distillation column, and so on. Okay, so you need to know how you can implement this inherently safer design in the plant design. Okay, so what is ISD? Okay, we just go through. Okay, ISD is an inherent. Okay, it helps to eliminate or minimize the hazard. Okay, so basically inherent safety design is applied because it has the potential benefits. Okay, usually when you apply inherent safety design, when you apply or you implement this ISD towards your plant design, it will contribute to the simpler, cheaper, and safer plants. Okay, that's the ideal ISD. Okay, however, along with this lecture, you will know there are some give and takes towards the ISD implementation. Okay, so ISD actually is the philosophy or the way of thinking. It's just a tool that helps you in design. Okay, how you think or how it will helps you in determine how you develop your plant design. Okay, so it's just a way of thinking. So the definition of ISD actually is the design of chemical processes, okay, and products with specific attention to eliminating hazards. You try to eliminate hazards from the manufacturing process rather than relying on the control of this hazard. Okay, so one question for you: what is uh, what is the type of safety? Okay, what is the type of safety methods when you try to rely on this control of this hazard? Okay, so if you try to eliminate hazard during your design, that is called as a inherent. But when you try to rely on the control of hazard, what is it? Procedural. Okay, Junkit said that it's a procedural. Lagi else? Anyone? Okay, just using the chat box. Kalau you can also talk, okay, just unmute your mic and share your answer. Okay, so other than using inherently, okay, inherent or uh, passive method, okay, the relying on this control of hazard is actually is in active and procedural methods. Okay, it's belong to active and procedural method. Okay, while inherent and passive method is actually more towards uh, the designing. Okay, it's been towards design the plan or the process itself. All right. So this is the shifting of paradigm. Okay, the shifting of thinking in safety from previous. Wait. Okay. From previous traditional safety approach towards the ISD. All right. So during the early days of manufacturing plant, okay, they only have add-on safety features. Means only active and procedural methods. Okay, they only apply active and procedural methods. So they try to prevent the hazards. So they install alarms, safety interlocks, procedures, and training. This is active and procedural. Okay. They also try to mitigate the hazard by using sprinkler system, water curtains, emergency response, and procedures. So basically, the traditional safety approach more towards active and procedural. Whereas when you apply ISD, actually you try to eliminate the hazard first. Okay, you try to find the answer or try to find the solution how you can eliminate or even reduce. Okay, you try to reduce the hazard first before you can apply your active and your procedural. So the traditional involve active and procedural, while ISD actually involves starting from inherent, passive, active, and procedural. Okay, so there is two different paradigm or two different way of thinking during your traditional approach and your ISD approach. So when you talk about ISD, okay, it is actually try to eliminate or try to reduce the hazard. So hazard, okay, as we know from our first class, okay, from our first class of process safety or plant safety, is what is hazard. Okay, so actually hazard in ISD is the inherent physical or chemical characteristic. When we said about inherent physical or chemical, it is involved the potential for causing harm to people, environment, and property inside the thing itself. Okay, when you said about hazard, inherent hazard, it actually have been packaged. Okay, it has been built up with this hazard. Okay, when you said about benzene, okay, actually the benzene itself already contain the hazard. So how you can reduce or you can eliminate this hazard from the benzene? You can eliminate the benzene or the hazard from benzene itself, but you can reduce the hazard inside the benzene by using, okay, some for example the moderation of operating condition. Okay, that's how we apply or we implement ISD in our plant design. So the hazard is the inherent physical and chemical where it's potentially can causing harm to people, environment, and property. So the hazard are intrinsic to a material or its condition of use. Okay, for example, there are three examples here, just like chlorine. Okay, chlorine by itself is the toxic by inhalation, but chlorine is useful. only it is toxic if you inhale it. Okay, same goes for gasoline. Gasoline is a useful material. However, it comes with a package of flammable properties. All right. So the last one is high pressure steam. Okay, even though it's only a water, but when you call it as a high pressure steam, it has a potential of energy. Okay, the potential energy due to pressure, high temperature. Okay, so it comes with the hazard. Okay, the water itself is not a hazard, but when you call as a high pressure steam, it comes with a hazard. So how you can reduce this hazard or how you can eliminate this hazard? That's the task when you are dealing with ISD. Okay, so when you talk about ISD, mostly ISD have been implemented in chemical plant. Okay, most of chemical plant will implement ISD in during their design. Okay, so there are many types of accident or many types of hazards. Okay, that have been considerate have been in consideration when you are implement it. Okay, among the types of accidents actually or the types of hazards is fire and explosion, toxic gas release, steam and other hot material release, chronic exposure, okay, due to toxics, radioactivity, carcinogens, mutagens, and so on. And also lastly, the workers accident, okay, the one that involve with personnel, okay, workers accident during construction, maintenance, and operation. So all of these hazard must be included during your analysis when you are dealing with ISD. All right. So, all right. Okay, Junkit said about Bhopal. Okay, what do you want to share with us about the Bhopal, Junkit? Can you relate the Bhopal incident with the ISD? All right. Okay. You want to share some information regarding Bhopal? Okay. So the Bhopal actually have a MIC release. Okay, toxic gas release is related to Bhopal. All right. So actually, all chemical incident can be related back to the ISD. Okay, how their failure to implement ISD have contributed to the severe accidents. Okay, what a tragedy. Okay, so later on we will in gas dispersion topics. Okay, we will look further how we can estimate what type of severity of this accident. Okay, we try to uh, determine how far this gas can go when there is a gas release. Okay, so that will be our next topic of the process safety management. Okay, we have a toxic release and also fire and explosion. So never mind, we will look into these cases later on. Okay, Chernobyl is more towards radioactive. These types of accident, radioactivity. Okay, chronic exposure to radioactivity. Okay, it's quite a discussion there. Okay, regarding the reduce in volume and the concentration. All right. Basically, there is a give and takes towards the volume and also the concentration when you're doing when you try to implement ISD. So ISD will help us to achieve safer operation, reduce numbers of engineered safeguards. It can help to reduce the complexity when you try to apply your simplification techniques. You try to reduce the components and vessel size, and also it can help in reduce energy consumption. Okay, these are the advantages when you are implement ISD in your plant design. Okay, so if you read the article, it talk about Flexborough. Okay, how the incident in Flexborough, England, makes the ISD uh, as the method to be implemented during your plant design. Okay, so this is another case. Okay, Flexborough. I think have you learned this Flexborough incident with Dr. Azam? All right. Okay, you already learned about the Flexborough. So, what type of chemicals that involved inside the incident? Anyone forgot? Okay, cyclohexane. Okay, the cyclohexane vapor cloud. Okay, have make this have been the main cause for this disaster. Okay, around 50 ton of cyclohexane involved during the explosion. Okay, you will look then later on you will look how this cyclohexane can be developed into the vapor cloud. Okay, when you talk about vapor cloud, it is a huge explosion. Okay, you will learn about VCE, vapor cloud explosion, later on. Never mind. Okay, this is just a revision after what you have read throughout your article. Okay, so something to ponder around. Okay, how could a better design have avoid this disaster or reduce its impact? And will it be possible to eliminate the hazard altogether? Okay, so maybe the better design could help us to avoid the disaster, or we can tell that surely a better design can reduce its impact. Okay, that's for sure. Okay, a better design or ISD can help in reduce its impact. But could it possible to eliminate the hazard altogether? Anyone? Can you give your opinion regarding this statement? Will it be possible to eliminate the hazard altogether? You can talk, okay? You can unmute your mic and your friend can hear your voice, okay? If you are lazy to type, okay? Izudin is, I think depending on the type of hazard, okay, very good. Yankee, yes, if can, we can find a substitution of chemical. All right. Anyone else? Ada lagi tak? There is around 93 participant here. Anyone? Nah kata takat orang sama. Yang lain? Banyak lagi ni nama. Did I need to pick any one of you? Your senior already know about the wheel of names. Okay, the wheel of names where I pick randomly the one that can answer the question. Anyway, okay, never mind. Okay, never mind. Okay, we don't have the face-to-face class, so actually it's quite impossible to recognize all of you. Okay, from Akil Ashraf, he said that it is impossible to eliminate all hazard. Okay. Alright, nanti tak apa. Kalau ni last, next time I will try to try to create this wheel of names. Alright, so basically the answer is just like Izrin said, it depends on the type of hazard. Okay, it depends on the type of hazard. Okay, but true. Okay, it's either we can eliminate all these hazard. Okay, but you need to remember that for Junkit, that you said that if we can find the replacement or the substitution for that chemical, you need to remember that usually when you are dealing with chemical, the chemical itself is the hazard. Okay, that's the intrinsic characteristic. So when you're changing from one type of chemical to another type of chemical, usually you just reduce the impact or you try to reduce the hazard. However, you cannot eliminate the hazards inside the chemicals. Okay, but it is possible to eliminate all the hazards together after you are including the inherent and also the passive and active procedures together with this inherent. So the answer is yes and no. Okay, it's depend on your chemical, your process, and your plant design. Okay, together with what type of methods that you apply. Okay, Junki said yes, impossible for all, but possible for one. Okay, we can eliminate one type of hazard, but it will create another type of hazard. Okay, that's it. Okay, thank you for your participation. All right. So this is the layer of protection that I've shown you during our last meeting in Telegram. Okay, you have your ISD here. This is the first layer of protection for your plant design. All start here. Okay, this is during your design. Okay, your design of your plant. Then you have your control, supervisory, preventive, mitigative, barrier, limitation, and response. So all these layers of protection belong to the active and procedural method. Okay, this is belong to the active and procedural methods. So your ISD in the first layer, okay, is the basic of the layers of protection. Okay, so definitely ISD will start the layers of protection. Once you get your best design of ISD in the first part, then the later part will come easy. So this is the ISD implementation flowchart. Okay, you start with you identify your hazard and you assess your risk against the risk management, and then you apply your ISD strategies. Okay, you apply your ISD strategies, then you apply your layer of protection. After you apply your inherent, then you apply your layer of other protection. Okay, so basically the first part or the first order of inherent safety is you try to avoid or you try to eliminate the hazard. Okay, when you try to eliminate the hazard, okay, this is the first layer. You try to eliminate the hazard first. Okay, because this is the way of thinking. You try to eliminate first. Even though we know that we cannot 100% eliminate all the hazard, we try to eliminate at least one hazard, just like JK said. Okay, we cannot, it is impossible to eliminate all the hazard, but it is possible to eliminate at least one hazard. Okay, try to avoid one hazard or a few hazards, then you can try to reduce the other hazards for their severity and their likelihood. Okay, the severity and likelihood will be learned later on. Okay, how you can calculate the severity and the likelihood of the incident or the hazards. Okay, so this is the first layer you try to eliminate. Then the second layer of inherent safety is you try to reduce the severity and the likelihood of the hazards. Okay, finally you apply your layers of protection. You apply your passive, active, and procedural safeguard. So this is the layers of protection. Okay, the first and second one is during your ISD, and then the passive, active, and procedural comes later. Okay, for your layers of protection. So if we go back to the early about the traditional ways of thinking or traditional ways of protection, then you know that you only apply your active, your passive, active, and procedural layers only. So you lost, or you at least you have reduced your layers of protection inside the inherent, okay, inside the ISD part. Okay, so this is the strategies for your protection. Okay, strategies for your protection starting from your inherent, passive, go to the active, and finally to procedural. Okay, I don't want to elaborate more towards these strategies. We already discussed it. Okay, it's already inside your article. What is inherent, what is passive, active, and procedural. All right. So inherent is try to eliminate and reduce the hazard. Okay, this is the explanation. I think this is actually the extraction from the article itself. Okay, how you can substitute water for a flammable solvent. Okay, or you can change the latex paints with the oil based paint in your plant. Okay, then you have your passive. Okay, how the passive is more depend on your design. Okay, design features itself. Okay, the passive method is depend on your design features. Okay, when you're dealing with 5 bar reaction, you develop, or you design your reactor within 10 bar punya capacity. Okay, the 10 bar capacity. So actually you have the margin inside your reactor. That's for passive uh, procedure. Okay, that's the passive strategies. Okay, you have inherent, passive, and then active. Active is more towards the control. Okay, how you can control, or using the instrument system. Okay, you have your uh, sensors, you have your signal control, you have your decision making device. So that all of these are active. Okay, active means you need to install third party equipment. Okay, so the active part is you need to install other things to inside this equipment. Okay, if you remember, there are some words that what we call as a gold plated. Okay, gold plated equipment. Okay, you already design it, but after you operated it, you know that, oh, you need another safeguard here, another control here, another safeguard down there. So that's a gold plated. All right. That's what is mean by the active. Then you have your procedural. Okay, lastly, after you have installed your active, you install your uh, active method, then you have your standard operating procedures. Okay, this is your SOP. Actually, SOP, the one that you're dealing with inside your uh, lab. Okay, do you remember your not the control lab? Okay, control lab. Then you have your unit ops. Okay, you have your SOP, right? That's how you try to prevent any hazards. Okay, you need to wear helmets, you need to wear shoes. Okay, your lab coat. That's already one part of layers of protection. Okay, if something happens, you already been covered. Okay, that's the last part of the layers of protection. So that layers of protection is depend on you. So either you want to follow or not. Okay, just like COVID-19 SOP, say JK. Okay, means that when you're dealing with something, the procedural or SOP is the last layers. Okay, just like COVID. Okay, COVID-19. The government already released the SOP. Okay, because we already know in PKP. Okay, so in PKPB, is all depend on you. Okay, there is less restriction towards you, so all depend on you. You are the last layers of protection. If you lost it, then you already lost another layer of protection. Okay, so inherent duduk diam-diam di rumah. Okay, JK said, alright, never mind. Okay, that's the four strategies. So which strategy we should use? So when you are in the early part of your development of your plant design, okay, you can apply inherent, then you apply your passive, active, then procedural. So when you are dealing with multiple hazards in a chemical process, the same strategy could be used. You try apply the inherent, eliminate at least one or two hazards, then you can apply your passive, active, and procedural unless, until you can minimize or you can reduce the impact or the hazard itself. So basically, we should use all these these four strategies. Okay, inherent, passive, active, and procedural. The one that we said is a IPAP, IPAP. All right. So this is the flowchart of question. Okay, because ISD is the ways of thinking. So you need to think. Okay, you found some hazards. Okay, inside your equipment or your process or your plant design. Then you start to ask yourself, can I eliminate this hazard? Okay, just work from one hazard to one hazard. Okay, look for one hazard, can I eliminate this hazard? If you can eliminate this hazard, meaning that you already apply your SD, maybe you make a substitution. So when you make a substitution with another chemicals, you ask yourself again, did anak saya nangis dekat luar pintu ni, dia nak masuk bilik ni. Alright. Okay, biasalah sound effect belakang. Okay, can I eliminate this hazard? Okay, when you make a substitution, then you ask yourself again, this new material or these new chemicals, is it have a new hazard? Okay, that's why I say that when you make a substitution, maybe your substitution contain new hazard, but maybe it is less severe. Okay, or the hazard itself is reduced. Okay, so if you can eliminate the first hazard, but the second or the substitute materials or chemical, it will introduce a new hazard, then you can apply your passive, active, and procedural. If there is no new hazard, then there, okay, you can proceed with your design. Okay, same goes to the question of can I eliminate this hazard? If the answer is no, okay, you ask again yourself, can I reduce the magnitude? If you cannot eliminate the hazard, is it possible for you to reduce the magnitude of the hazard? If the answer is no, then you need to introduce the layers of protection. Means that it goes back to your passive, active, and procedural. But if you can reduce the hazard, is it contain new type of hazard or the hazard itself already been reduced? Okay, sometimes when you introduce some ISD to reduce the magnitude of the hazard, you also introduce new type of hazard. But the same solution is still go back to the layer of protection. Meaning that actually the ISD is the inclusion of your inherent. Okay, you try to eliminate or reduce the magnitude first, then you try get your help, the other helps from the passive, active, and procedural. Okay, so inherent first, then try, if the inherent itself is not enough, then you introduce this passive, active, and procedural. Okay. So inside the inherent itself, okay, inside this inherent, okay, this is the inherent part. We have another 4 strategies. Okay, previously is the safety strategies. Okay, layers of protection strategies. This one is the ISD strategies, inherent strategies itself. We have substitute, minimization, moderation, and simplification. Okay, you already know the definition by the videos that I already upload inside the uh, Telegram. Okay, you already know what is substitution, minimization, moderation, and simplification. So minimization when you try to use small quantities of hazardous substance, okay, from maybe two barrel of chemicals, then you reduce to 1 barrel of chemicals during your process. Okay, that's how you try to minimize your quantities of hazardous substance or material. Okay, the minimization inside the ISD sometimes also relate to the process intensification. Okay. Yeah, I will upload this lecture in e-learning also. Okay. Don't worry. Anything that involve the lecture will be uploaded in e-learning. Okay. It's either e-learning or Telegram. Okay. So the process intensification itself will relate to the minimization of ISD. Okay. Apart from the benefit, application, and example. Okay, process intensification. What is intensification process? It is any chemical engineering development that leads to a substantially smaller, cleaner, safer, and more energy efficient technology is a process intensification. So, if involve the smaller, cleaner, and safer, okay, this is the one. This is the definition of ISD in minimization. Okay, you try to create a chemical process with use a substantially smaller, cleaner, and safer process. Okay, so that's how the process intensification will relate to the minimization. Okay, minimization strategy. So the however the process intensification itself is a lot more than only the minimization. Okay, it involves about the parameters and also processing methods, uh, units. Okay, it involves the combination of processing units, operation condition, and also the substance itself. Okay, that's how the process intensification works. So there are benefits when you apply the minimization. The first one is to reduce your consequence of incident, and the second one is when you try to improve the effectiveness and feasibility of the process. Okay, when you reduce the consequence of incident, you actually talk about the incident of fire, toxic release, explosion, and so on. Okay, when you are using less numbers or less quantity of hazardous material or flammable material, you already reduce the consequence of fire incident or explosion incident. Same goes to the toxic material or toxic substance. Okay, when you reduce the concentration or the quantity of that material, you already reduce the consequence of incident. Okay, for the toxic release. So when you apply your minimization, okay, it also improve the effectiveness and feasibility of the process. Okay, because when you apply your minimization, you actually reduce the usage of your secondary containment, okay, maybe your reactor dump, and also the quench system are longer not be needed, okay, because you already minimize your material. Okay, there are many types of minimization process or minimization strategy that you can apply. For example, for your storage, piping, and process equipment. Okay, for piping lines, maybe you can minimize the line size or you can minimize your line length. However, you need to take a consideration into a consideration of is it good enough as a uh, to that process. Okay, so the mechanical integrity need to be accounted for. Okay, you need to consider all this integrity about the mechanical, about the safety specification, and so on. You don't want to jeopardize the safety. Only you want because of you want to introduce the inherent minimization in your process. Okay, you don't want to jeopardize that. Okay, so maybe for storage, when you apply your minimization, maybe you no longer needed your storage. Maybe you only use the just-in-time deliveries, meaning that once your raw material coming, okay, from your supplier, then you directly use it for your process. What we call that's what we call as just-in-time deliveries. It comes through that the material coming to your plant, then you take it and directly use it. So you don't have to store the material or the substance for a long period of time. Okay, because uh, the longer the time you retain the material inside your area or inside your plant, there is a higher chances or the higher probability of the incident occur. Okay, you also can minimize the inventory by phase change. Okay, you can use the liquid instead of gas. Okay, so that you can minimize your storage capacity. Okay, the process equipment just like the one that been given in the article, how you can eliminate the process or you can eliminate the byproduct process. Okay, so that you don't have to store the byproducts. Then this is the substitution, how you substitute a less hazardous with the alternative material. Okay, so when you're dealing with a substitution, you usually is involved the toxicity, the flammability, and the reactivity of the material. You try to reduce this part. Okay, you try to reduce the toxicity, flammability, and reactivity of the material. Okay, so we will give some benefits and then we will look about what is the application example of this substitution. Okay, for example, you can substitute from using gas with hot oil for your heat exchanger, then you can replace it with the gas and hot water for your heat exchanger. So actually you already replace or substitute your hot oil material with your hot water. Okay, but you must make sure that the capacity of heats inside this heat exchanger is same. Okay, is comparable. Okay, this is the example of using the substitution, how you can change from solvent base. Okay, for example, in coatings and paints, how you can change from the solvent base to the water base. Okay, and how you can try to substitute or try to find a replacement of alternative way of moving product. Okay, for example, for transportation, maybe instead of using lorries for transporting your material, maybe there is a pipeline, okay, to transfer this material. Okay, because there are some chemical plants that have been located nearby. Okay, maybe the same company with this specific plant, but their location is have been separated. So they will use a transportation like lorries or trucks to transport the material from one plant to another plant. So maybe as a substitution, you can implement the water pipe, the piping lines, okay, underground, okay, underground piping line to transport the material from plant A to plant B, okay. But there are other things that need to be considered, okay, when you try to implement this ISD. Later on, we will look what is their trade-off between your ISD implementation and the real situation. Okay, these are the benefit. Just same like the previous one, it will help in reduce the hazards, actually the fire hazard, toxicity, and also the odor. Okay. Okay, for example, this is the reaction of acrylic esters. Okay, the process of acrylic esters, what we call as a RAPE process. Okay, RAPE process usually use acetylene. Okay, using acetylene with carbon monoxide and alcohol. Okay, the production of acrylic esters, if you are using this RAPE process, we involve the flammability materials for acetylene, the toxic and flammable material for carbon monoxide, also with the combination of material as a nickel carbonyl, we call is a toxic to the environment, uh, heavy metals with carcinogenic properties, and also the HCl, okay, anhydrous hydrochloric toxics, which is corrosive, okay, anhydrous is a corrosive. Then the output itself or the product itself is a monomer with a reactivity. Okay, so basically this process is good. However, the hazard inside this process are too much. Okay, the hazard inside this process are too much. So when you are introducing ISD, okay, you have your alternative chemical reaction. Okay, you have your alternative chemical reaction, what we call as a propylene oxidation process. Okay, propylene oxidation process. So this propylene oxidation process, it does not eliminate all the hazards, but it is inherently safer. Okay, inherently safer. What we call as a inherently safer, the comparison between the previous process and this process, this is less severe. Okay, because the hazard are primarily flammability, but we already reduce some of the chemicals that have been used from the previous process. Okay, we already reduced, but the the hazard are still there. We only reduce some hazards. Okay, that's how the substitution strategies works in this ISD. Because once we cannot eliminate all the hazard, we try to eliminate at least one hazard. Okay, for example, the refrigerant alternative. Okay, in early days, we are using ammonia, SO2, and light hydrocarbon for our refrigerant. We are using this material inside the refrigerator in early 1930s. However, this ammonia, SO2, or light hydrocarbon is very toxic and flammable. Okay, the uh, the quantity of hydrocarbon inside this refrigerant also quite huge. Sometimes it goes from 1 to 3 kg of light hydrocarbon inside the refrigerator. Then, after 1930s, CFC have been discovered. Okay, chlorofluorocarbon have been discovered. So, it is apparently during that time, CFC can be considered as the inherently safer alternative for ammonia, AC2, and hydrocarbon. So, starting from 1930s, all the refrigerator have been built and using CFC as a refrigerant until 1980s, when we know that CFC actually what CFC have contributed to. Yes, okay, depletes ozone layer. Okay, depleted ozone layers. So after that, we discovered that, oh, we try to substitute this CFC. After 50 years of using CFC, later on the refrigerant need to be substitute. Okay, need to be replaced. So one part or one of the solution is using light hydrocarbon. If you remember, light hydrocarbon also have been used in early 1930s. But during this time, this light hydrocarbon actually have been reduced. So from light hydrocarbon, okay, light hydrocarbon have been replaced by CFC, but later on CFC have been replaced back by light hydrocarbon. But during this time, this light hydrocarbon have been minimized, okay, from 1 kg or 2 or 3 kgs to only 120 gram. Okay, so this involve, the first one is the substitution, but if you look back, it actually is a minimization. Okay, you minimize the numbers or the quantity of light hydrocarbon. Okay, so actually it's already reduced from kgs to just 120 gram of hydrocarbon. Okay, if you look at the back of your refrigerator, there will be a tank, okay, where the refrigerant already been stored, okay, behind your refrigerator. Okay, that's the hydrocarbon that will be used for your refrigerant. Okay, then we have a moderation. Okay, it's already 12:30. Okay, we have a moderation. Okay, moderation is try to have a less severe processing condition. Okay, for example, we introduce the dilution. We try to dilute from the aqueous to anhydrous, or from the dry benzoyl peroxide, for example, towards the wet benzoyl peroxide. Okay, so this moderation strategy is works more towards the operating condition. Okay, towards the moderating condition and also the parameters. Okay, how you can reduce the concentration and so on. Okay, so for example, this is the reaction, the pressure inside a reactor. Okay, in early 1930s, usually the reactors works towards up to 600 bar. Okay, then it reduced to 300 to 350 bar. Later on in 1980s is only around 100 and 150 bar. So actually when you minimize or you reduce the pressure inside the your operating condition, it lower the when you are lower your pressure plant, when you lower your pressure operating condition, your plant will be operated in cheaper, efficient, and much more safer. Okay, maybe in towards 2020 and above, maybe the pressure already decreased or reduced until below 100 bar. Okay, that's when we introduce many type of catalysts and so on to speed up our process. Okay, and finally, the fourth strategy in IST is using simplification. Okay, simplification. Okay, just like how these piping lines have been installed. Okay, we try to simplify. Okay, we try to eliminate unnecessary complexity. Okay, maybe actually all this pipe is redundant. Okay, when you try to eliminate unnecessary complexity, we actually try to reduce the risk of human error. Okay, when you try to reduce the human error, actually you also contribute to the example to the, I think the slide have been it's been duplicated from the moderation. Okay, my bad. Okay, simplification actually when you try to eliminate the unnecessary complexity. Okay, you try to make it as a straightforward process. Okay, for example, for connection, elbows, bend, and joints for fitting, you try to simplify all these piping line. Okay, or instead, for example, you try to for vessel or for your column, okay, you try to separate and divide it. Okay, instead of using single complex multi-purpose vessel, maybe you can introduce a very several simpler processing step, or vice versa. If there are too many simple processing step and vessel, why not just introduce one type of vessel? Okay, there is give and takes between this approach or this strategy. Okay, eliminate, how we can eliminate the rated design, how we can eliminate the auxiliary equipment. Okay, instead of using wires now, everything is now in wireless. Okay, you have your uh, earphone that have been wireless. Okay, wireless earphone. You have wireless charger. Uh, Even now you are using wireless internet. Okay, back to the early 2000s. Okay, in hostel, all students are using cable. Okay, LAN cable, local area network cable. Now everyone are using wireless. Okay, now Junki said about 5G. Okay, even 5G is not already been utilized, fully utilized. They already start to discover the 6G and 7G. Okay, that's how the technology works. It moves faster than the application itself. Okay, so this is the give and takes in how you can implement your uh, simplification strategy. Okay, for example, this is the one of the best example that you can find out for your simplification process. Okay, this is the methyl acetate distillation process. Okay, this is the distillation process. You have a reactor and you have a few columns. Okay, you see you have 1, 2, 3, 4, 5, 6, 7, and 8 column. Okay, you have 8 distillation column, 1 reactor, and extractor. Okay, so this is the previous. Okay, then this is the one after you introduce your ISD. Okay, so now the process only have one distillation column and two extraction column. Okay, one is to remove the impurity And another one is to reduce or to extract the heavy metals. Okay, instead of you have your flash column, axial column, solvent recovery, and so on. Okay, when you introduce this simplification strategy, you now have fewer vessels. Okay, you have fewer flanges, fewer valve, pumps, instrument, and less piping. Okay, as you can see, the difference between these two types of design. Okay, you have the first design and the second design. But when you look back, now you all have a very complicated distillation column. Okay, so instead of using simple column, now you have a very complicated column. But there are only few columns as compared to the 8th column. Okay, so that's why I say that there are give and takes during your ISD implementation. Okay, so now your reactive distillation column itself is more complex toward the previous one. You have multiple unit operation occur within one vessel. Okay, instead of you have your specific or dedicated extraction column. Okay, for metal acetate, then you have your solvent recovery, you have your water extractor. But now you have multiple unit operation occur within one vessel. Okay, it will be more complex to design. Even though this looks simple, but it will be complex to design because it involves difficult control and operating condition. Because this extraction column will depend lots more on operating condition. How you try to eliminate or extract all this material. Okay, all this material are depend on your operating condition. Okay, because the distillation process itself is a temperature dependent. Okay, it depends on your pressure and temperature operating condition. So maybe some say that maybe we can go back for a simpler column. So which one did you want to use? The first design or the second design? Anyone? If you are designer of this metal acetate plant design, which type of plant operation that you will choose? The first one or the second one? Uh, Most of you have choose the second design. Okay, but some of you are using the first design, less complex. Okay, so basically it depends on what is your objective and how you want to achieve it. Okay, if you already have your specific plan or you have your dedicated plan for each of the uh, material, then you will choose the first one. Okay, meaning that when you are dealing with, okay, this, there are pro and cons actually for the first plan and the second plan. Okay, it depend on your justification. Okay, for example, okay, for the first plan, when you involve all this equipment, okay, you need to remember that this is less complex to the previous one. Okay, that's a pro of this plan. However, you need to consider all the operating procedures during this process. Okay, when you are operating this plant, now you have 8 columns that been operated. Okay, consistent have been operated, and you need to remember that all these column have their own hazard. Okay, all these column have their own hazard. So the hazard already been double up as compared to the previous the second design. So that's the contra of the second plant design. However, for the second plant design, it is more complex, meaning that when they're dealing with the complex process, the severity of hazard also increase. Okay, the severity of the complex also increase. Okay, so there is a give and takes. What do you want to do with your plant? Okay, if your plant is have been covered by layers of protection, for example, active and procedural that are quite TikTok, then it is good for you to have this complex design. Okay, because you already been what we call not insulated as have been covered, okay, by a layers of protection after this design. Okay, so basically there is a conflict and trade-off during your ISD. Okay, it's either some material is hazardous, but it is also useful for that purpose. Okay, for example, gasoline is flammable, but it have the ability to store a large quantity of energy. So until now, if there is no replacement of flammable material that can store the quantity of the same quantity of energy just like gasoline, gasoline will still be useful. Okay, gasoline will be used inside the process. Okay, so for example, car. Okay, for our transportation, we will depend more on diesel and petrol. Okay, because the price itself and how it can store a large quantity of energy. Okay, even though now there are already introduced electric car, but what the quantity of energy between this electric car and the diesel or petrol based engine car, there is some gaps between there. So as long as the diesel and petrol car have not been the replacement of this source of energy is not been discovered, we will still use this material. Okay, so there are some conflicts, okay, between each either this is hazardous and its useful properties. Which one is much more bigger, hazardous or the useful properties? Okay, so even though you have the hazardous material, if you can control the hazard, so you can use it to gain the benefits, just like gasoline. Okay, if you can control the hazards of the flammability, then you have the ability to gain the benefits of this gasoline. Okay, so what is the ability to control the hazard? So you know the gasoline have the flammability limits. What is their lower flammability limit? What is their upper flammability unit? Then using this information, you can create a control system so that the process will not exceed the limit itself, so that you can still use the gasoline and gain the benefits of its useful properties. Okay, the second conflict is about the multiple hazard. Okay, some material coming with the toxicity, flammability, corrosiveness, reactivity, and so on. It has a multiple hazard inside the one or the same materials. So for industrial application, you need to rely on inherent, passive, active, and procedural risk management strategies. Meaning that for multiple hazards operation, you need, okay, you must apply all of your safety strategies. Your inherent, passive, active, and procedural. Okay, so that you can use this material even though it have a multiple hazards. Okay, the last conflict or the trade-off is some material have the multiple impacts. Okay, if you are handling, for example, the chlorine uh, material, okay, chlorine, okay, you have a 1 ton of 1 ton cylinder of chlorine versus a 90-ton rail car of chlorine. Okay, so if you change your type or you change your approach of how you dealing with this chlorine, okay, now it will give the multiple impacts. Okay, the impacts when you are using the cylinder and the impacts when you are using 90 ton of the rail car to transport this chlorine. Okay, so the impacts actually can be reduced or it's depend on your safety technologies option. Okay, because some uh, option, even though the impacts is high, but the technology will help to reduce the impact itself. Okay, so these are the conflicts and trade-off when you are trying to implement ISD inside your plant design. Okay, this is something that there are no right and wrong, okay, during your implementation. Okay, only your justification when you are choosing the right strategies. Okay, when you are choose the strategies for your ISD, there come your justification. Everything that you choose must be justified. Okay, so your justification will involve these conflicts and trade-off. Okay, the example for previous justification, the previous conflict and trade-off is the when you try to reduce the size of hazardous material storage tank in a plant. Okay, this is the scenario. You try to reduce size of hazardous material storage tank. Okay, so that instead of using 150,000 kilogram rail car, okay, yang macam just like a train tu, okay, rail car, we call it a rail car, okay, we using trucks, okay, instead of using rail car, we are using trucks, so you will only transporting around 15,000 kilogram of material for one truck. Okay, so you already reduce the amount or the quantity when you are transferring this hazardous material. Okay, instead of 150,000, you're only transporting just 15,000 of material. But when you are using this type of approach, you're already reducing the hazard for this quantity of material. Okay, when you reduce your quantity of material, you are reducing you are reducing the hazard itself. But when you look back, you need at least 10 trucks to ship the same numbers of material, just like the rail car. So these 10 times of truck also have their fatality rate. Okay, so you need to consider again. Okay, so this is the one that you need to justify in using rail car or trucks. Okay, rail car versus trucks. You need to consider everything. What is the fatality rate for the road and the rail car. Okay, so you are using trucks. What is the fatality rate for the trucks of transporting this hazardous material? What kind of roads that you are dealing with? Is it a very busy road, or uh, some turfy roads? Okay, then you also need to consider when you reduce the site risk. Okay, you already reduce the site risk. This is the site risk from 150,000 to 15,000, but you already increase your society risk. Okay, because the shipment, okay, your trucks will use the roads where everyone also use the same roads, so you already increase the risk for society. So this one also need to be considered. Okay. Then again, what's about the supplier larger inventory? Okay, when you are dealing with 150,000 kilogram rail car, then the supplier inventory usually will be higher. So your supplier or the one that receive the supply from you need need to have 150,000 capacity in their storage. That's the issue. So your storage tank also need to can be dealing with 150,000. The receiver also need to have 150,000 capacity of this hazardous material. Okay, instead of using 15,000 material, but you are transferring it in 10 days. Okay, every day you're transporting 15,000 kilogram of this material. So what is their fatality rate? So all of these are things that need to be considered. So it's either you reducing your risk or you transferring the risk from your side to the other side. Okay, from your side risk to the society risk. Okay, yeah. The rail car usually the one that been used by YTL and other cement industries. Okay. Okay, last slide for 2 minutes. Last 2 minutes. All right. The ISD misconception. Okay, the misconception is when you thought about ISD will eliminate all the hazard. Okay, this topic will already been discussed. Because ISD will not eliminate all the hazard, but you can eliminate all the hazard with the combination of ISD and other safety uh, approach. Okay, just like active, passive, and procedural procedures. Okay. So the ISD represent the best approach to managing a particular hazard. You must always implement that design. No, not every design must implement all the ISD. It depends on your justification. Okay, but the best is you try to implement first ISD during your design. Okay, so there come the third misconception. ISD only applicable at early stages of process research and development and plant design. No, ISD is not only applicable at early stage. It's not only during your design. After you're operating your plant also, ISD can come later. Okay, ISD is the ways of thinking. You always think about your safety of your plant. Okay, there is always a way where you can reduce or eliminate all the risks and hazards. Okay, then the misconception is about the plant operating personnel have little to contribute to implementing ISD. No, plant operating personnel or the one that's dealing with that plant or that equipment itself have a large more contribution on implementing ISD because they have their opinion. They know what is the best when dealing with this equipment or process. Okay, just for example, like the trucks and rail car tadi. Okay, the previous rail car and trucks scenario. Okay, the one that dealing with transportation know how difficult when you are transporting this material using trucks. You have another possibility of the trucks breakdown and so on. Okay, and finally the misconception of ISD is there is a best technology which is always inherently safer for the manufacture of a particular product. Okay, because there are not always a best technology. Okay, because the technology itself will depend on your uh, objective and your justification. Okay, technology is there, but you need to justify, is it best for you or not? All right, so this all about the ISD. Okay, later on, for our next class, okay, because next week is your semester break for your Hari Raya. Okay, then your the previous weeks is your test during your 2 hour session. Okay, Dr. Azam will take charge of the class on Wednesday, where he will conduct your test one. All right, the detail of the test will be uh, explained by himself, but I just want to tell you that for this week, next week 25 until 29 is your semester break for Hari Raya. Then when you come back for 1 of June, there is your tutorial session. There is no tutorial session. Then Tuesday is my part. Okay, is my class, 1 hour class. Then Wednesday 3rd of June is your test one. Alright, remember. Okay, balik kampung juga. Yang mana boleh balik kampung lah, kalau kampung dalam negeri yang sama. Okay, but on your 3rd of June there is your test one. Alright, okay, any question? Any question? So we will meet again on 2nd of June with a new topics. Okay, with a new topic of process safety management. Any question? If not, okay, selamat Hari Raya for those yang selamat Hari Raya, and happy holidays for the one that been at home. Okay, thank you for joining. I'm really sorry for our first 30 minutes of difficult connection. Okay, thank you for listening, and I will upload this video in either Telegram or e-learning. I will announce later where I already upload this video. Okay, thank you for joining me. Okay, selamat raya and happy holidays. Okay, goodbye.